Hi everyone, and welcome to this lecture on chapter 12. So still here in unit 3, talking about the micronutrients. I believe this is our last chapter for unit 3. So in this chapter, we're going to be talking about some of the micronutrients that function in blood health and blood cell formation. And we'll talk a little bit at the end of this chapter about different micronutrients that support our immune system. So we will spend the majority of this lecture talking about blood. So the first few slides will just be a little overview of blood as one of our tissues, one of our organs, basically. So it is like the fluid or liquid organ or tissue in our body. So blood, let's see, a couple main functions here. So blood acts as, I think I've referred to it as like a highway before. So it's a means of transporting nutrients, including oxygen, to different cells and different organs throughout the body, right? Things travel in our body through the blood from one place to another. And then, so yeah, specifically transporting nutrients and oxygen. Blood will also transport waste products. So we've started to talk just a little bit over the last few weeks about, especially in our metabolic processes, some waste products are generated just naturally. Just like if you're following a recipe, cooking a meal, you're going to have some waste products, whether it's like a wrapper from something you bought, or it's the ends of your vegetables that you aren't going to put in the food. So in a similar fashion, all the processes, all the metabolic processes that happen in our bodies throughout the day generate waste products. And so those need to get removed from the body. And again, blood will be the transportation area, I guess. Things will be transported through the blood to be removed. And then we also have white blood cells, which all function in our immune system. So white blood cells support the immune system, or are components of the immune system. And then we also saw really briefly that blood is also a means of transferring heat throughout the body. So we spoke really briefly in the hydration lecture about sweating and evaporative cooling, and how as we sweat, blood that circulates close to the skin is going to be, we're going to be giving off water as part of evaporative cooling. And so that process will cool the blood that's close to the skin, and then that blood travels back to the heart and back throughout the rest of the body. So in that way, we start to send cool blood throughout the body. So it can be a means of transferring heat. And that works in the opposite direction too. As we kind of warm up, blood circulates that heat. So 4 components of the blood, 4 different types of cells, basically. We have erythrocytes, leukocytes, platelets, and plasma. So erythrocytes are the red blood cells. So these are the ones that are really critical for transporting oxygen. And then leukocytes categorize all the different white blood cells that we have. Platelets are basically like cell fragments that assist in blood clotting. So platelets are for clotting. And then plasma, we also touched on this briefly when we talked, also when we were in the hydration lecture, or the water and electrolytes lecture. Plasma is the fluid portion of the blood. So the plasma is the part of the blood that is directly correlated with blood volume. And then this one is figure 12.1 from your book, just showing you, this would be your blood, like if you gave a blood draw, if you had blood drawn, it would all be kind of homogenized and mixed together. But then if you were to separate, and you wouldn't necessarily do this, but in a laboratory, the blood could be separated out effectively by weight. And so you'd see some of the heavier particles would drop to the bottom. But then you can also see the relative proportions of the different components of the blood. So you'd see the majority of blood is in that plasma form, so that fluid portion. And then next most abundant is the red blood cells. So 45% is the erythrocytes. And those two combined, the plasma and the erythrocytes, makes up 99% of your blood. So then the 1% that's left is a combination of platelets and leukocytes, or white blood cells. All right, here's a quick overview of the different micronutrients that we'll talk about for blood health. And you'll notice vitamin K, B6, folate, and B12 are all vitamins we've talked about already in reference to other body systems, but they're so critical also in this system of maintaining healthy blood that we revisit them here. And then iron, zinc, and copper will be relatively new. We haven't really said much about these three. I will not really go over this, but this is, again, just a helpful quick reference for the RDA, so the dietary reference intake values, the RDA, or that adequate intake, or the tolerable upper intake level. So anything I do want to point out here? I don't think so, but you'll notice that with many of these, especially the minerals, as we age, you'll notice that the RDA will go up a little bit. And typically that's because we absorb less well as we age. Okay, so we'll start with iron, and there'll be a lot to say here about iron. Iron is kind of the highlight, I guess, of this lecture. So again, you'll note your textbook will kind of remind you which ones are trace, which minerals are trace, and which minerals are major. Worth starting to pay attention to that terminology. I'm just not going to ask you to remember which minerals are trace and which minerals are major. But trace is simply meaning that we have less iron in the body and we require less iron relative to some of the major minerals, such as calcium or sodium, magnesium. So here are some various functions of iron, right? Maybe the most important ones are these two that kind of go together. Iron makes up this compound called heme, which is a central component of red blood cells that carries oxygen. So in erythrocytes, we have this large molecule called hemoglobin, and at the center of hemoglobin is heme, and at the center of heme is iron. And so that's the oxygen carrying component of our red blood cells. Then we also have like a form of red blood cell called myoglobin, which specifically carries oxygen to the muscle cells. So start to kind of think of hemoglobin and myoglobin together. They have a very similar role of transporting oxygen in the blood. And then again, heme would be the central component of that. Other functions of iron. So we didn't really learn this term cytochrome, but when we talked about the metabolism, that last phase of metabolism, which is called the electron transport chain, actually involves a lot of cytochrome molecules. And it's actually the cytochromes that do the transferring of electrons, and therefore the transferring of hydrogens, that allows us to actually ultimately make ATP. So iron is a critical component of those cytochromes. So that means iron is critical actually for that last step of energy production from the macronutrient. And then iron also supports some of our antioxidant enzyme systems. So remember in the antioxidant lecture, we learned that there are various enzyme systems that support antioxidation. So iron is critical for some of those enzyme systems. And then iron is also important for DNA synthesis and cognitive development. So pretty critical functions here for iron. And then here is like a visual representation of hemoglobin, myoglobin, and heme down here in the center. And then again, you can see right in the center of heme is iron. Iron is abbreviated Fe, if you remember from the periodic table. That's maybe the first one we've seen that is different from the spelling of the name. So Fe representing iron, and again, iron sits at the center of that heme compound, and then heme is a critical component of hemoglobin and a critical component of myoglobin. specifically for the purpose of carrying oxygen through the blood. Again, kind of like many of these other micronutrients we've talked about so far, we always want to be maintaining a certain amount of iron in the body. So this concept of iron homeostasis speaks to, having adequate amounts of iron in the body at any given time. And so in order to do that, the body has to regulate the digestion of iron, the absorption of iron, the transportation through the body, the storage, and the excretion. Just like we've seen with something like calcium, and even like glucose, one of our macronutrient building blocks. So depending on the status of iron in our body at any given time, our bodies will sort of automatically alter iron digestion and alter iron absorption. And then there are also some things maybe external to the body that can affect how we digest and how we absorb iron. So an external factor, for example, would be, the amount of iron in a given meal. So again, just like we've seen with some of our other micronutrients, the more iron in a meal, oftentimes the less we will absorb. We'll also see that the amount or the type of iron, there's a few different types of iron, basically like forms of iron, but still iron, but it can kind of exist in different forms. So depending on the form in which it's occurring in our food, that will affect absorption. And then we'll talk about some other factors of the diet that can either enhance or inhibit iron absorption. So those would be external factors affecting digestion and absorption. And then these last two here, right, like our body status of iron. Again, usually if we're lower in iron, so if we have a poor or a low body status of iron, the body's going to absorb more iron from the food, and vice versa. And then also we're going to see that stomach acid is necessary for digesting most of the iron that's in our food. So having, a healthy stomach, making adequate amounts of stomach acid is going to be critical for iron absorption. So here's when I say that there's two types of iron in our food, here's what I mean. We have well, this is part of what I mean. There's more to say on a coming slide. So we have heme iron and non-heme iron. And every day we're starting to learn a little bit more about both types of heme and non-heme. So a real simple overview here is that heme iron is typically found in animal foods, so meat products basically. And this is also, a lot of the heme in our bodies is also in this heme form, right, in the heme and hemoglobin and myoglobin. And we can actually absorb heme itself pretty directly. So that's helpful. So we can absorb heme iron quite readily. And then non-heme iron we find in plants, and then we also are going to find non-heme iron in animals. Again, we have non-heme iron in our bodies. Even if we just go back here to the different functions of iron, when iron works as a cytochrome or supports the cytochromes, when iron supports antioxidant enzymes, and when iron supports DNA synthesis and other cognitive development processes, iron is not in heme form here. So we always have a lot of non-heme iron in the body, and same with other animals. So that's what this is getting at, right? Heme iron is just iron bound up in that heme compound, and non-heme is, basically free form iron that's available in the body for other functions. So in foods that we eat, the majority of iron is in that non-heme form. 85 to 90% of all iron that we eat is in non-heme form. In animal-based foods, we're going to see higher proportions of heme iron, again, just because of the hemoglobin and myoglobin. But it's still, potentially even 50-50, we're getting heme and non-heme iron from animal-based foods. So some of those external, this is both external and internal factors that are going to enhance iron absorption. So like we said, stomach acid, and I'll show you a visual of this coming up, but these are two, oh, I'm sorry, I didn't update the, that's funny. I put the plus sign in superscript, but I forgot to put the number in superscript. So there's these other two ionic forms of iron. You could say Fe3 plus and Fe2 plus, or you could say ferric and ferrous. So ferrous is the Fe2 plus, and ferric is iron 3 plus. So actually down here, the ferrous form absorbs a little more readily than the ferric form. And so some things like vitamin C, if there's vitamin C in a meal, that actually helps convert the ferrous form, therefore making it more, making more iron more readily available. And then the stomach acid as well does the same thing, reduces the ferric to the ferrous form, which is more readily absorbed. Some things that impair iron absorption. So these compounds that we find in some of our plant foods, phytates, polyphenols, and oxalic acid. Iron can be bound up in these compounds, and so then there's going to be less to absorb. The good news is cooking basically breaks these things down. So we don't usually go around eating raw legumes or raw rice, or even rarely do we eat raw whole grains. So perfect. Just by cooking these foods, which we have to do anyways to make them edible, we break down the phytates and make the iron more available. Polyphenols, so these are another form of phytonutrient. So these are actually really beneficial to us for other reasons. But these are things like you would find in many herbs, red wine, like green teas and some black teas, and also coffee. But just be mindful if you're having like a high amount of any of these things. I actually worked with somebody who was having 3 cups of green tea a day, and that did seem to be impairing iron absorption. So it's also it's a matter of how much, right? That's always going to be a factor in nutrition. But just be mindful, the polyphenols can interfere with iron absorption, especially if you're having a lot. So be mindful of your coffee intake if you are a heavy coffee drinker. 1 to 2 cups of coffee is recommended per day. Remember, a cup measures 8 ounces. And then oxalic acid, similar to phytates, we find oxalic acid in some of our green vegetables and also some grains. But again, cooking will break down the oxalic acid and therefore make the iron available. And then also some other minerals. If we're taking in high amounts of these other minerals, and actually, I think maybe it's supposed to say manganese. I'll make a note for you guys. Check your book too. I feel like that's a typo. But it may not be, because these are all divalent cations. Divalent meaning having a charge of 2, right? Di meaning 2, and cation, do you remember if that's positive or negative? Cation means positive, right? So zinc, magnesium, and calcium can all take on that 2+ charge, just like iron. So if we have, again, high, I would say excessively high amounts of zinc, magnesium, I'm going to put manganese in this group too, or calcium coming into the body at any given, at the same time that we're ingesting iron, these may actually compete with each other for absorption sites on the enterocyte. It seems to be, again, hopefully you're noticing this theme. This is especially true if we're taking a high dose supplement at the meal when we're eating an iron-rich food. So it doesn't seem to be such an issue if these other minerals exist in the food itself. It really seems to be if it's that high dose supplement form. And then just a little blurb about bioavailability. For what it's worth, bioavailability of iron from a vegan or vegetarian diet is approximately 5 to 10%, versus a typical Western diet, the absorption is going to be a little higher. And that's simply because in a Western diet, we're consuming more heme iron. This is not to say that you cannot get enough iron from a vegan or vegetarian diet. You absolutely can. It's just saying that we absorb a little bit more, not even a lot more, but we absorb a little bit more from an omnivorous diet. And then transportation of iron in the body. So we're going to see, again, I keep mentioning this visual, I guess I put it at the end here, but we'll see that there's this transport protein called ferroportin. And if you think about portin, like port, maybe you think of like a door almost. So ferroportin is on the enterocyte. So it actually regulates the absorption of iron into the enterocyte, as well as the release of iron then into the rest of the body. So ferroportin is kind of like that door into the enterocyte and out of the enterocyte that says, you know, depending on the body status, if the body has enough iron, we don't need to absorb a lot of iron. So it might only open the door so much. But if we are really low in iron, then maybe ferroportin says, okay, yeah, let's absorb much more iron because we're low. And then transferrin, so start to think of like even right here, even transfer, but that starts, this is actually the ferrin, the ferric is referring to the iron. But transferrin, this is like a true like shuttle bus. So this is transporting iron in the blood. So it's the transport protein for iron in the blood. And then we're further going to have some regulation at the site of the cells. They're going to need another, iron is going to need another receptor on the cell membrane in order to be absorbed into the cell. And then we also store iron. So again, this is all part of the maintaining and regulating the homeostasis of iron. So we do store some. The primary storage form is what we call ferritin. And this is an important one that gets looked at to assess the stages of iron deficiency. And then we also have kind of an overflow form for iron storage, which is called hemoseridin. And we store iron primarily in the liver. We can store a little bit in the bone marrow, the spleen, and also in those enterocytes in the small intestine. Okay, so here's the visual. It's figure 12.3. So this kind of summarizes a lot of everything we've just talked about. So up here, this is showing the two different ways that we can get iron. Well, this is actually two of the ways that we can get iron from our food. We have non-heme. So we have non-heme and then we have heme iron, right? So the heme iron gets absorbed pretty easily. We can actually absorb heme itself right into the enterocyte. The non-heme iron, so non-heme iron is going to be that ferric or that ferrous iron. So if there's ferrous, which is Fe2+, that's the one that gets absorbed a bit more easily. And you'll notice too, when the heme globule breaks down in the enterocyte, the iron is in that ferrous form. And so that can be readily absorbed into the blood. And remember, ferroportin is that kind of that door that allows the iron into the body, depending on how much iron we need. Non-heme iron, coming back up to the top, non-heme iron can also be in that ferric form, Fe3+. Ferric iron we can also absorb directly, but it just seems to be a little bit of a less efficient or slower process. And if we're going to store iron, we'll often store it in that ferric form. So we can store ferritin, and remember hemoseridin is that kind of overflow storage. And the enterocyte is a place where we can store iron. And then in the blood, you'll notice transferrin, transfer for transport. We also transport iron typically in that ferric form. And then up here, it's showing you that some of the iron may be bound to those polyphenols, to the phytates, and to the oxalates. And so some of it may get lost in our feces. Okay, so a little bit of review here. So absorption of iron depends on how much is in the food the body status, so how much is needed, and then any of those other dietary factors that might affect absorption. Also going to be influenced by stomach acid. So actually the person I had referenced earlier who was having 3 cups of tea a day and seemed to actually be having low iron status, that person actually had had a stomach surgery and so was not producing a sufficient amount of stomach acid. So failed to mention that there was another factor affecting iron absorption in that case, because they were not producing enough stomach acid to assist in that conversion of ferric to ferrous. So we lose iron throughout the day. Some of it is just the turnover of those small intestine enterocytes. So remember, we're storing iron here. But remember, these enterocytes don't live forever. So if it comes time to, break down these cells and build new cells, if there's iron stored there, we're going to actually lose that iron. So this concept of turnover is breaking down old cells and building new cells. So again, we can lose iron that way. Again, we can lose some iron in our feces. Menstruation for females is a time of pretty significant iron loss. And then anytime we're giving blood away, giving blood, so whether that's actually a traumatic physical injury with a lot of blood loss, that could be a time for major iron loss. But also anytime we do blood donations, we're giving away a pretty significant amount of iron. We do recycle iron, which is pretty cool. But again, we don't recycle enough to make it a non-essential nutrient in the diet. But as we break down old cells elsewhere throughout the body, we will recycle some of that iron. But again, some of it will also be lost. So the recommended, I missed one. The recommended intake for iron, it varies. So the RDA varies by age and I should say sex. I'm sorry about that. For males, it's about 8 milligrams per day. For adult males, for adult females, it's about 18 milligrams per day. And that's ages 19 to 50 during those years of menstruation. Yeah, so you'll see that's quite a bit higher for females than for males. Also during pregnancy, iron requirement goes up significantly, and that's due in large part because of the pretty significant increase in blood volume that occurs with pregnancy. And then food sources of iron, so certainly any animal foods. Liver, of course, can be a good source of iron because that's where animals also store some iron. And then this says enriched and fortified cereals and breads, which is true. And you can also get iron from some whole grains and some legumes. And then, of course, supplements could be a source. Let me just go here real quick just to give you the visual. So here's the RDA for males. Up here's the RDA for females. Let's take a look. So lentils, 1 cup of cooked lentils would just about meet the requirement for males. Spinach can be a good source of iron. Again, beans, this is tomato puree. So if following a plant-based diet, again, iron, you do have to be pretty mindful of making sure you're getting enough of those iron-rich foods. But legumes are a great source of iron. You just need to make sure to eat enough of them. Okay, so then coming back here, circumstances that will affect iron status. So on the left, these are things that improve the iron status, again, meaning the amount of iron in the body. I'm not recommending the top one, but as a mean, I recommend oral contraceptives, but not necessarily as a means of reducing your iron loss, and I don't actually recommend the oral contraceptives that reduce menstrual blood loss. But anyway, that's not my role in this job. But for females who are using oral contraceptives that do reduce menstruation, that's going to reduce blood loss. So this is kind of a weird thing to say, that using oral contraceptives that inhibit having a period would improve your iron status. But this is from your textbook, so take that as you will. Breastfeeding will also delays menstruation. So that's also going to reduce blood loss. And then consuming iron-containing foods, of course, would improve body iron status. Okay, that's an interesting column. And then over here on the right, things that diminish iron status. So using hormone replacement therapy, this won't necessarily reduce iron status, but depending on, I would say, the quality of the hormone replacement therapy, it can cause uterine bleeding, so that would be, blood loss. I'm going to kind of say a maybe on the vegetarian diet. It doesn't necessarily diminish iron status, so that's kind of maybe a poorly done vegetarian diet, like an Oreos-based vegetarian diet would be, could certainly lead to reduced iron status. Then these three down here are maybe a little more realistic. So if you do have a parasite infection in the intestines, especially a pretty severe one, that could cause intestinal bleeding. So that could certainly lead to reduced iron status. Again, blood donations, like we said, you're giving away blood, that's going to reduce iron status. And then also it seems that intense endurance exercise training can also reduce iron status, but this doesn't mean that the person is forever at a reduced iron status. Again, if you couple intense endurance exercise training with eating iron-rich foods, it should be okay. But it seems to be that the increased inflammation could be a cause of reduced iron, and then potentially seeing an increase in like the rupturing of red blood cells and that sort of red blood cell turnover maybe is a potential means of losing body iron, potentially increased in fecal losses. But again, the intense endurance exercise training can be coupled with a really healthful diet, and then you shouldn't be at a major risk of having a poor body iron status. I don't know how much I like this chart. I'm not going to star it, but take a look if you like. Alrighty, what happens if we have too much iron? Again, most likely is coming from supplementation. It's pretty hard to eat too much iron. Interestingly, one of the most common causes of poisoning deaths in children is due to accidental iron overdose. Again, that's only going to come from oversupplementation. So less severe iron toxicity, I guess, would include symptoms like nausea, vomiting, and diarrhea, right? Basically, your body trying to expel or get rid of that excess iron. If this goes on for a long enough period of time, we develop something called hemochromatosis, which is basically having like excess iron storage. Again, largely usually due to excessive iron supplementation. Let's see. And there are some like other mineral deficiencies that can cause symptoms similar to hemochromatosis. For example, copper, we'll see. How do you treat too much iron or iron toxicity? Primarily just by reducing your dietary intake of iron, reducing use of iron supplements, potentially also avoiding high vitamin C intake, because remember, vitamin C enhances iron absorption. You could donate some blood. You can also use some chelation drug therapies that will actually chelate or pull iron out of your body and help you remove them in the feces. And what happens if we don't have enough iron? So this is actually more, I'd say, I guess, more common and potentially more life-threatening. So iron deficiency is the most common nutrient deficiency in the world. That's a fun test question. People at the highest risk are infants and young children because, again, such a rapid period of growth, so much increased blood production can be, more at risk of not getting enough iron to meet the needs. But then you'll also see, and forgive me, I didn't change these wordings, adolescent females, premenopausal, and pregnant females. So again, these are all periods of greatly increased blood production and blood needs. Other causes or contributing factors to iron deficiency would just be not eating enough, having excessive blood loss, potentially eating, like if it's possible, too much fiber or having too much phytates in the food. But again, that would be from eating a lot of raw grains, basically, and raw beans, which most people aren't really doing. Anything that's going to reduce stomach acid production. So this we're seeing a lot more commonly now with more and more surgeries to the digestive tract, also bariatric surgeries. And then anything else that's going to impair iron absorption. So just poor gut health overall, if those enterocytes are not healthy. And then again, over-supplementation of some of those divalent cations, again, like calcium and zinc. Okay, and then iron deficiency has what we call 3 stages to it. So I've got 2 pages here, actually 3 pages to go over this. So stage 1, we call this iron depletion. Stage 1 is pretty easy to go unnoticed because there are no physical symptoms yet. Because basically what we see in stage 1 iron deficiency is a reduction in the storage iron, right? Hemoglobin itself is not going to be affected because we're going to pull iron out of storage to give iron to the hemoglobin for our blood. And so we're not really, it's easy to miss stage 1. What you will notice though, if the doctors look for it, would be reduced levels of circulating ferritin. Right? Ferritin is that storage, one of the storage forms. And so if you test for ferritin, you might notice that it is decreasing. If there were any symptoms at all, it would just be reduced energy during like high intensity things. So like, I don't know, if you were like running up a hillside or something, if that was part of your regular weekly endeavor, then maybe you would start to notice like reduced energy in doing that, but maybe also other like high demand, like even cognitive work, like if you have a very demanding job or a very, very demanding day, just having sort of less energy to do that, but still subtle enough to go unnoticed. So stage 2 is typically where we start to pick things up. Stage 2 is also called iron deficiency erythropoiesis. So in stage 2, we start to see a decrease in the saturation of transferrin. Remember, transferrin is the transport protein for iron in the blood. So decreased saturation of transferrin with iron. So we see transferrin carrying less iron. What goes along with this is actually an increase in something we call total iron binding capacity, or TIBC. These are also things that can be looked for on blood work. And this should make sense because total iron binding capacity simply means the total capacity for transferrin to bind iron. So as your body status decreases and there's less iron available to bind, that's going to increase iron binding capacity. So hopefully that makes sense. Transferrin is going to be transporting less iron, but total capacity to bind iron therefore goes up. And then you'll definitely see a reduced work capacity in stage 2. Again, remember that iron, one of its primary jobs is to help transport oxygen throughout the body. So if you have less iron, you have less oxygen to help in those metabolic productions that generate ATP. So you start to see diminished work capacity in stage 2. And then in stage 3, this is where we can diagnose iron deficiency anemia, which we also call microcytic anemia. So anemia, this is also, at least I think, it used to be a common test question. I can't remember if I still have it in there. But the word anemia literally means, quote, without blood. Like that's the original meaning, whether that comes from Latin or Greek, means without blood. Now, quite literally, of course, you still have blood, but the blood isn't functioning. The blood isn't right? So that's what we mean by this concept of without blood. It's, you could insert a little caret there and say without healthy blood, if that sounds better. So in iron deficiency anemia, we see a decrease in red blood cell total amount, so decrease in quantity. We also see a decrease in the cell size, and that's what this term microcytic means. Remember, micro means small, and cytic refers to cell, right? So microcytic meaning small-celled anemia. So small cells decrease in quantity. That's definitely going to lead to a decrease in hemoglobin levels. And so this is where we really start to have some pretty serious symptoms. So smaller than normal red blood cells. Iron deficiency anemia can also be identified by the change in the color. So iron deficiency anemia also results in hypochromic red blood cells. So hypo also meaning lower, and chromic referring to the color. So there's a lesser red color to the red blood cells in iron deficiency anemia. So symptoms here would be, again, fatigue, like greatly reduced work capacity. You would also start to notice a paleness to the skin because of this hypochromic component. The immune system is also going to weaken, cognitive function, nervous system, memory, and again, work performance, all of that's going to decline. If this is happening during pregnancy, we're going to see low birth weight infants, potentially premature delivery, and unfortunately, potential for infant or maternal mortality. This is just a helpful overview. I won't really spend any time here, I guess, but just make a note of actually what's happening in the body in the different stages, and if there are physical symptoms or symptoms at all. And do also start to make note of what anemia actually, what that word means, and then start to identify the differences in the different types of anemia, because we're going to talk about anemia several more times in this lecture. So they don't really highlight it on this page. So come back here and make sure you understand these two components of iron deficiency anemia. Okay, so that's just mineral number 1. Now we'll talk about zinc, which is the second mineral for this chapter. Zinc is also a trace mineral, and zinc has a lot of jobs, kind of like magnesium. So kind of like magnesium, zinc is a cofactor for more than 300 enzymes throughout the body. And here's an example of several of those. So zinc supports alcohol metabolization. Zinc supports food digestion. Carboxypeptidase is one of the protein digesting enzymes in the small intestine. Zinc also supports bone formation, and zinc supports red blood cell synthesis, or heme synthesis specifically, which is why it's in this chapter. Zinc also supports structural integrity throughout the body. So I think kind of interestingly, in our DNA, we have these binding proteins that are called zinc fingers. And zinc fingers, so they use zinc, and these specific binding proteins, or these zinc fingers, actually affect protein shape, which is part of genetic expression, right? Remember, genes in the DNA code for proteins. So genes are basically the instruction manual for building proteins in the body. So some of the proteins that these zinc fingers affect would be some of the vitamin A receptors in the eye, so supporting vision, so helping build those. Also, some of the hormone receptors on our peripheral body cells for vitamin D and thyroid hormones. So that's really interesting, right? If you have a zinc deficiency, you may actually be having issues with your thyroid and your vitamin D homeostasis as a result, because you don't have proper receptors to actually absorb these nutrients into the cell. Zinc also supports antioxidant work, coupled with copper. Zinc and copper work together in this copper-zinc superoxide dismutase, which is one of our antioxidant enzyme systems. And then zinc also supports activation of immune cells and kind of, again, that structural integrity of immune cells. And then kind of as a third category, zinc also has some regulatory functions. So specifically here would be gene expression. Again, similar to zinc fingers, but slightly different. This is actually turning on or off genes. So zinc actually is part of the processes that say this gene will be expressed and this gene won't be expressed. So again, all coming back to protein synthesis. And then zinc also supports cell reproduction and growth. And that's just a little bit. That's just a cliff notes of zinc. Now we'll talk a little bit about zinc absorption, and I do have another diagram to share with you. So in the small intestine, in the enterocyte of the small intestine, we have metallothionein, which is basically a storage protein for zinc. And so just like we saw with iron, our body status of zinc at any given time is going to regulate how much we absorb into the enterocyte and ultimately into the body. So as we saw, zinc is really important for genetic expression, cell reproduction, growth, heme synthesis. So anytime we see growth, sexual development, pregnancy, you're going to see and kind of an increased need for zinc. So absorption is going to increase during those times. And then I'm going to switch back to highlighter. And then again, just like we are seeing with other minerals, certain things will affect zinc absorption, either to inhibit it or to enhance it. So things that might inhibit our absorption of zinc, again, this works in both directions. So non-heme iron intake can compete, so that ferrous iron can compete with zinc absorption. And then also, just like we saw with iron, phytates in our food, like whole grains and beans, can impair, they can be bound to the zinc and make it less available. But again, cooking reduces these phytates, so zinc becomes more bioavailable to you. And then it seems that apparently animal-based proteins enhance zinc absorption. So figure 12.6. Again, just like with non-heme iron, we do need stomach acid to separate zinc from proteins in the diet. So that's, again, going to be an important component of zinc absorption. And then here, again, zinc being a divalent cation. So zinc can be absorbed in two ways, either via a transport protein on the enterocyte membrane, or zinc can also come in via active, sorry, not active, like this would be facilitated diffusion, and then this would be just regular diffusion. Again, depending on body status. So we can store zinc right there in the enterocyte as metallothionein or as a component of metallothionein. And then there would be another zinc transport protein at the, what would be called the basolateral membrane of the enterocyte, absorbing it into the bloodstream. Zinc is transported by albumin in the blood. And then again, we might see some zinc loss depending on the intact fiber content or phytate content of the food. Zinc is a trace mineral, so the requirements again are pretty small. 8 milligrams for females, 11 milligrams for males, slightly higher for males. The tolerable upper intake level is suggested at 40 mg per day. Food sources, so again, meat can be a source, whole grains, small amount from legumes as well. And then again, apparently we absorb a little bit better from animal foods with the animal protein. So let's see, they're just going to show a fortified whole grain here. Yeah, so RDA for males, again, like a this is interesting, a cup of pork and beans. Also, your mixed nuts are going to give you some zinc. So RDA for females, 1 cup of mixed nuts would almost meet the RDA for the day. Small amounts from dairy products. If you do like an omnivorous diet, especially if you like oysters, obviously just 3 ounces of raw oysters would far surpass your zinc needs for the day. And too much zinc. So again, toxicity is pretty much only occurring from supplementation. Again, you're going to see intestinal pain, cramps, nausea, vomiting, all things that are indicating that your body is trying to get this excess zinc out of you. Prolonged exposure to too much zinc can actually impair the immune function. We're also going to see again, an interference with copper and iron absorption. And potentially zinc can also impair our HDL, or high density lipoprotein concentration. So while it's cool that you can get so much zinc from raw oysters, again, too much of anything can be detrimental. Right? Too much of a good thing can be bad, I guess you could say. But again, mostly we see excessive zinc in the body from oversupplementation. And then also, this is probably one that goes unnoticed, pretty well unnoticed, is not enough zinc or zinc deficiency. Part of that is because we lack good assessment tools for zinc body status. So some of the things that could be looked for, potentially hair loss, also impaired appetite. That's a big one. Increase in infections. Those would be some of the earlier signs maybe. And then also potentially diarrhea. And then during periods of growth, potentially growth retardation in children or adolescents, and also potentially delayed sex maturation. Alrighty, and then copper. So copper, also a trace mineral. In the body, copper primarily exists as ceruloplasmin, and so this is the laboratory assessment for body status of copper. Functions of copper, so iron transportation, and again, I roughly mentioned this before. So if we have a deficiency of copper, we can actually have iron deficiency anemia because we're not properly getting iron to the places out of storage and where it needs to go for use. So that's really interesting, I think. And you'll start to notice this. There's never really a straight line to figuring out these assessments, or when somebody presents with symptoms, it's really not a direct. You have to kind of look at several different stages and several different areas to really figure out what the true underlying cause of the deficiency is, or what the true underlying cause of the symptoms are. So copper also works as a cofactor in energy metabolism. Again, with zinc, so we have that copper zinc superoxide dismutase, which is an antioxidant enzyme. And then copper also seems to regulate neurotransmitter production, for example, serotonin. So again, things that are going to increase copper absorption from the gut. Again, the lower the body status of iron, and also the less iron copper that's in the food, the more we'll absorb. So we see this with pretty much all these minerals. And then factors that are going to impair copper absorption. If there's a high amount of copper in the food, we'll absorb less. But also zinc and iron can compete with copper binding sites on the enterocyte. So again, like if you're taking an iron supplement or a zinc supplement, those could potentially interfere with copper absorption. The RDA for copper is just 900 micrograms per day, so less than a milligram. Copper is pretty abundant in our foods, again, especially organ meats, seafood, nuts and seeds, and whole grains. Start to notice whole grains are a pretty nutritious food in the whole grain form. So here's the RDA for males and females, less than a milligram. Oysters, again, would be a great source. Nuts would be a great source. Mushrooms, potato, beans, spinach. Right, so copper is pretty available in our food. So deficiency is relatively rare. So here's copper deficiency, again, rare. Symptoms, again, could be anemia, right? If there's due to an interference with iron transportation, not necessarily copper deficiency anemia, but copper deficiency induced iron deficiency anemia. You can also see a reduction in white blood cell count, potentially also osteoporosis. And again, you might see that iron build up in the tissues. So sort of like hemochromatosis. And then too much copper. So we don't know as much about too much copper at this point, but there is something called Wilson disease, which is a disease that results in liver damage due to like excessive copper intake. So again, the symptoms of too much copper are going to be the same that we're seeing: abdominal pain, nausea, diarrhea, vomiting. Your body is trying to expel this excess nutrient. Alrighty, and then we'll start talking about the vitamins that are involved in blood health and blood synthesis. So these are all review vitamins, actually. We talked about these vitamins in other functions of the body. So vitamin K, remember, is one of our 4 fat-soluble vitamins. We talked about it already with regard to bone health. And now we'll talk about it here for blood health pretty briefly, though. So remember that vitamin K acts as a coenzyme to different proteins. And we talked about some of the, like the GLA proteins that vitamin K acts as a coenzyme for in bone health regulation. So this is that same concept. So vitamin A acts as a coenzyme for some of our blood coagulating proteins. So specifically prothrombin uses vitamin K, and then there are also several different types of procoagulants that use vitamin K to function. So remember that vitamin K is produced by bacteria in our gut. Yeah. And then dietary needs are going to be based on your intestinal health. So if somebody has, some form of gut dysbiosis or just doesn't have a healthy gut for whatever reason, there may not be enough bacteria to produce enough vitamin K. Also from our diet, remember, if there's any issue with fat absorption, so any gallbladder issues, any liver issues, vitamin K may not be absorbed very well because it's a fat-soluble vitamin. And also broad spectrum antibiotics are going to very likely kill off the bacteria that would produce vitamin K. So again, the recommended intakes, significantly less than 1 milligram for females, so 90 micrograms, and then 120 micrograms for males. At this time, there's no established upper limit. Again, food sources can be your green leafy vegetables, and also soybeans, and you wouldn't really eat canola beans. Canola comes from the rapeseed plant, so canola oil, or the oil of the rapeseed, could also be a source of vitamin K. Again, we don't know so much about having too much vitamin K, but we are starting to be more familiar with vitamin K deficiency. So far, to our knowledge, it's relatively rare, but of course it's going to result in failure to clot, right? So we're going to see excessive bleeding or potentially hemorrhaging. Fat malabsorption, again, would be a cause of vitamin K deficiency. And remember that newborns typically would get an injection of vitamin K at birth because they lack the intestinal bacteria that produce vitamin K. Okay, and then we're going to review 3 of the B vitamins. So B6, folate, and B12 we're going to review. So B6 is essential for heme synthesis. Remember, we talked about B6, folate, and B12 in the metabolism lecture. So these vitamins also support energy metabolism. So B6 is an integral component of that heme complex. RDA for adults is 1.3 mg per day, And again, as we age, the RDA will go up. Again, usually associated with decreased absorption as we age. So take in more with the hopes that you absorb more. B6, let's see, food sources would be meat, poultry, fish, also soybeans and any soy-based products. Starchy vegetables can be a source, and then again, whole grains or fortified cereals. We do see toxic effects, especially with supplementation, and that seems to have most prominent effect on our nervous system. So deficiency of B6, in this case, we're going to talk about B6 anemia, basically B6 deficiency anemia. So it's going to impair red blood cell production, and again, also would impair protein metabolism and neurotransmitter production. This, I think, is a really helpful picture. So figure 12.9 in your book. So this is just showing, right here in the middle is showing healthy red blood cell production, right? So red blood cells are made from stem cells, and under health, in a healthy body, you're going to have all of the right micronutrients needed to develop that red blood cell, and it'll look kind of like a nice donut, or like a what's that new type of peach? I guess it's called like a donut peach. Those little peaches that sort of look like a little donut. Okay, and then in either direction, it's showing you that without adequate micronutrients, we're either going to wind up with macrocytic anemia, right? Macrocytic red blood cells, macro meaning large, cytic meaning cell, right? So large-celled red blood cells, or we'll end up with microcytic anemia. Micro, again, meaning small, cytic meaning cell, so small-celled red blood cells. So what can cause each of these two things? So folate and B12 go together. A deficiency of either can cause macrocytic anemia. And again, it's really important to notice if you're faced with a client or a family member or whatever, a patient who has macrocytic anemia, it could either be a B12 deficiency or a folate deficiency. So we say that those two can mask the deficiency of the other. And then if we have microcytic anemia, that can be iron, as we saw. That can also be B6. And remember, that could also be copper-induced iron deficiency anemia. So in either case, with low iron, copper, or B6, you're going to see microcytic anemia. Alrighty, so folate, let's see. So folate we use, used for all forms of food, folate with biological function. You might also see folic acid, either in supplement form or in enriched and fortified foods. So functions of folate, it again also acts as a coenzyme, supports DNA and amino acid synthesis, supports cell differentiation and division, and again, works with B6 and B12 in metabolism and extracting the energy from our macronutrients. The RDA for folate is 400 micrograms a day for adults, and it does go up during pregnancy, and even starting before pregnancy, it's worth making sure, if somebody is planning a pregnancy, it's worth making sure you're getting this much folate prior to becoming pregnant, because the birth defects associated with folate deficiency occur in that first trimester. So you don't want to be, several weeks into a pregnancy, realize you're pregnant and realize you're folate deficient. Ideally, you start the pregnancy having excellent stores of, or excellent status of folate. So fortification, many foods are now fortified with folate because the health effects to the fetus and to the infant of folate deficiency are so severe. So you might be familiar with neural tube defects like spina bifida. These are due to folate deficiency. So many grain foods are now fortified with folate, I guess because people eat a lot of processed grain foods in this country. But many of our real foods are also going to be jam-packed with folate. So eating unprocessed food would also give you adequate folate as long as you eat them. So again, I think I mentioned in the metabolism micronutrient lecture, spinach and your leafy greens would be a great source of folate. Lentils and other whole grains can also be good sources of folate. Asparagus and also liver potentially could be a source of folate too. So folate deficiency, we'll talk about folate deficiency and B12 deficiency. So there are 4 stages, again, similar to iron. Iron had 3 stages, but again, it kind of follows a similar pattern. So in stage 1, you start to see blood levels of folate decline. So it's a little different from iron. We store iron, we don't really store folate. So by stage 1, you're already going to see blood levels of folate declining. By stage 2, you're going to see, again, low serum folate and also low red blood cell folate. Remember, homocysteine also is this component found in the blood that can contribute to cardiovascular disease, but can also be metabolized by B6 and B12. So if you start to see elevated homocysteine levels, that can be an indicator of stage 2 folate deficiency. And then the next stage would be stage 3, which is we would see erythropoiesis. I guess it's called folate deficiency erythropoiesis, but what we see is inhibited erythropoiesis. So we saw this term with iron deficiency, and I don't think I explained it, but erythropoiesis is the production of new red blood cells. So stage 3 folate deficiency, you start to see inhibited erythropoiesis. And then by stage 4, we have full-out anemia. So remember, folate deficiency anemia results in macrocytic anemia, so large-sized cells. And again, anemia, the original meaning of the word means without blood. So you're going to see basically non-functioning red blood cells, because when these blood cells get made like large and oblong shaped, they don't work as well, right? They're not doing their job correctly. So macrocytic anemia, meaning these sort of large misshapen red blood cells that can't do their job. So macrocytic anemia, larger than normal red blood cells, which inhibits their ability to transport oxygen. So symptoms are going to be similar to microcytic anemia. You're going to see fatigue, irritability, difficulty concentrating, headaches, shortness of breath, and reduced work capacity. Remember that symptoms can also result from the B12 deficiency because, as we'll see in a couple slides, B12 deficiency also results in this macrocytic anemia. So a little bit of B12 review. Again, it's a coenzyme for DNA synthesis. B12 can regenerate folic acid. And then again, alterations in B12 static can mimic those symptoms that we see in iron and folate deficiency. The RDA for B12 is 2.4 micrograms, also pretty small. Sources of B12, again, animal and meat products primarily, and then many foods are now fortified with B12. Remember, B12 is this one I said is also made by bacteria, but not bacteria that live in our gut, but theoretically like healthy soils, like this was where we would have originally gotten it from, is actually interacting more closely with healthy soils. Bacteria that synthesize B12 tend to live in healthy soils. And again, theoretically, potentially like a home gardener who gardens without pesticide or any sort of anything that would kill off the bacteria that live in the soil. Theoretically, could actually get some B12 exposure just by interacting with the soil and the microbes that live in it. Okay, so factors that are going to alter B12 digestion, absorption, and balance. So remember, B12 also requires proper stomach acid production. Remember, B12 requires that intrinsic factor. So any issues this is also why people who have undergone bariatric surgery should be on a B12 supplement for the rest of their lives. So any issue with stomach acid production is going to impair B12 absorption. Remember, the RDA for B12 is so low because we actually store some B12. So we actually have about 2 to 3 month supply of B12 in a healthy body. B12 deficiency also follows a 4-stage process, very similar to folate. So in stage 1, you're going to see decreased B12. By stage 2, you're going to see decreased B12 in the blood. By stage 3, you're going to see that you're going to see decrease in red blood cell production due to B12 deficiency, so inhibited erythropoiesis. And by stage 4, that's where we can diagnose B12 deficiency anemia, which again is a macrocytic anemia. So toxicity and deficiency. As far as we know right now, there are no major adverse effects of having too much B12, but obviously the symptoms of not enough B12 are pretty serious. So deficiency is actually increasingly common. I should change that. And of course, it's associated with dietary insufficiency and reduced absorption. Effects would be neurological effects. Lack of B12 can actually lead to improper formation of that myelin sheath around our myelinated neurons. And you can also see gastrointestinal effects from B12 deficiency. So the B12 deficiency is also referred to as pernicious anemia. So this is again a macrocytic anemia. Pernicious anemia is actually the end stage of an autoimmune disorder that results in lack of stomach cells, potentially leading to lack of stomach acid, and potentially leading to that lack of intrinsic factor. So B12 deficiency, again, can result from dietary insufficiency and can result from autoimmune disorders that affect stomach health or stomach cell production. All right, and then we'll start to shift gears here and talk about our immune system and our immune health. So we will not really get into much depth here in the immune system in this chapter, but kind of just a nice helpful overview and kind of a summary of some of all these micronutrients we've talked about and how they support the immune system. So in the immune system, right, this is the part of the body that helps protect us from infectious diseases. It helps us to heal our wounds, and potentially it guards against cancer development. We can basically say that we have sort of 2 parts to the immune system: our non-specific or our innate immune system, and we have our specific or our adaptive immune system. So non-specific is all of basically our primary defense mechanisms. So these actually really are happening all of the time. Our non-specific immune system is basically working all day. So our primary defenses against microbes, bacteria, viruses, airborne particles, toxins in the air, snake venom, and any ingested toxins that come in through our food. So again, non-specific is also called innate because it's the type of immunity that we're born with. So different parts of the body that act in non-specific immunity. Any mucous membranes, so your eyes, your nose, the back of your throat, even your vagina, and then skin, so your integumentary system. Also your stomach acid, remember we talked about the hydrochloric acid in the stomach helps to destroy any ingested toxins that come in with the food. Again, your tears, so again, your eyes are mucous membranes. Your saliva also, remember, has bacterial components in it. And then actions, so like coughing, sneezing, vomiting, diarrhea. These are also actions of the innate immune system or non-specific. So again, they're non-specific, meaning that it's your immune system reacting to general, it's just general defense. It's not specific to any type of foreign particle. So coughing, sneezing, vomiting, diarrhea, these again are all ways that would try to expel that foreign particle from your body. Non-specific immunity does use some of our immune cells, so macrophages, neutrophils, and natural killer cells. We're also going to see cytokines, which are chemicals that work in the inflammatory response. And so with non-specific immunity, we can see some of the pain associated with inflammation. We can also see loss of appetite, fatigue, and fever. These would be very typical symptoms of non-specific immune function. Here's just a nice picture of a macrophage engulfing an invading microbe. So this kind of gelatinous looking thing would be the macrophage, and all these little pill-shaped things would be the microbes. And then we have our specific, or what's often called our adaptive immune system. So specific because this part of the immune system will actually recognize certain components on the foreign cells, and we call those components antigens. So our bodies will recognize these antigens on foreign, again, foreign bacteria, foreign viruses, and will act specifically against those antigens. So again, just a little bit of overview of the immune system here. We have two types of specific immune cells. So we have B cells and we have T cells. B cells actually work in kind of identifying that antigen. So once we're exposed to an antigen, B cells can actually form memory cells, and memory cells will remain in our circulation theoretically for our lifetime, so that if we're ever exposed to that same antigen a subsequent time, we can react to it very quickly because we already remember how to respond to it. And this is really how vaccines work, actually. B cells can also form something called plasma cells, and plasma cells are the type of B cell that produce the antibody. So the antibody is the part of our immune system that can work on that specific antigen and actually help to activate the T cells, which are the immune cells that will actually try to destroy or deactivate the foreign particle. So T cells, we also have two types. We have cytotoxic and we have helper T cells. So cytotoxic, again, cyto meaning cell, toxic meaning toxic. So toxic to the cell. So cytotoxic T cells will destroy foreign particles. Helper T cells actually help to activate other macrophages from our innate immune system. Helper T cells also activate the B cells to form memory cells and more plasma cells, more antibodies. And then helper cells can also activate more cytotoxic T cells. So we can acquire a specific immunity in a few different ways. Again, vaccination is a form of acquiring specific immunity. Exposure, firsthand exposure to a foreign microbe would elicit specific immunity. We can also receive antibodies from our mothers, so from breast milk even, if we're breastfeeding. So we can acquire specific immunity that way. And then we can also acquire specific immunity from anti-serum injections, like if we get a snake bite. So that's just a sort of a super quick Cliff Notes overview of the immune system. So now we can kind of talk a little bit about when and where we see immune system malfunction, basically, and what the results might be. So when the immune system malfunctions, we might see that chronic inflammation, and we are also going to be more susceptible to infection. So when and why would the immune system malfunction? Allergic reactions are basically a malfunction of the immune system. Autoimmune disorders are also basically a malfunctioning immune system. When we're malnourished, so if we're not getting the right nutrition into our bodies, our immune system will also be weaker. And then immunodeficiency diseases, of course, are also going to result in a weakened immune system. And now we'll say a little bit about how nutrition supports the immune system. So again, a healthful diet is providing all of the nutrients that support the immune system. Single nutrient subclinical, so hard to notice deficiencies, can cause subtle abnormalities in the immune system. So even just one missing nutrient can affect how the whole immune system works. And then we'll also say a little bit more about protein energy malnutrition. This is protein energy malnutrition, meaning specifically not getting enough protein, can also reduce immune function. And then, of course, severe micronutrient deficiencies can reduce immune function. Infections can also affect nutrient status. So again, the total, the current status in the body of different nutrients. So infections can alter nutrient status by decreasing appetite. So depending on the illness or the infection, we might have reduced appetite, and therefore we're going to not take in enough calories or enough nutrients. Depending on the infection, there may also be diarrhea, vomiting, or inflammation. So that's also going to use up or cause us to lose nutrients. We also see an increased metabolic rate if there's a fever, right? Fever is actually contributing to, well, actually the increased metabolic rate is causing the fever, right? Higher body temperatures, more metabolic activity. So that's also going to chew up our nutrients more so. And then we might also, we're going to pull certain nutrients out of storage or even pull nutrients from different parts of the body to enhance the immune response. So at the end of the immune response, again, that can result in poor nutrient status in certain parts of the body. So here's protein energy malnutrition. So we haven't said this a ton, but many of our immune cells are protein-based cells. So if we don't have enough protein coming into the body, we're going to see a reduced immune response because we don't have proper cells or proper amounts of cells to have a fully functioning immune response. In particular, children who are experiencing a protein energy malnutrition or deficiency, we're going to see specifically reduced antibody production and then reduced ability of those cytotoxic T cells or macrophages to kill bacteria or other foreign invaders. So we'll see decreased immunocompetence, so basically decreased competency of the immune system. And this can be basically a pretty direct indicator of reduced nutrient status in the body. Obesity can also affect our immune system. So when we see obesity, we see basically a prolonged or that chronic inflammatory state, right? So what we're going to see is increased incidence of infection, delayed wound healing, and poor antibody response to vaccination or even to firsthand exposure to a virus or poor response to different bacteria. And part of all of that, again, is because of this chronic inflammation. So the immune system is constantly acting, so it's sort of tired, right? It's like if you had to just be running for 24, 48, 72 hours constantly, right? And then suddenly a bear started chasing you, you would already be pretty tired. So you'd have less ability to really run away from that bear or fight the bear or whatever. So that's kind of like what's happening in obesity and other chronic diseases, is we have chronic inflammation, so always happening inflammation. So then suddenly when a specific event happens, we have reduced ability to actually respond to it. So obesity basically can result in more severe asthma symptoms, hypertension, cardiovascular disease, and type 2 diabetes. A little review of our essential fatty acids. So you might remember in the lipids chapter, essential fatty acids are linoleic acid and alpha-linolenic acid. We metabolize these fatty acids into things called eicosanoids, which are basically signaling molecules. So remember, alpha-linolenic acid we convert to EPA and DHA, eicosapentaenoic and docosahexaenoic acids. And these are anti-inflammatory. Remember, these are omega-3s that reduce inflammation. So these can be really helpful in treating chronic inflammation. This is saying supplementing with EPA and DHA, but remember you can also consume EPA and DHA from cold water, saltwater fish, and you can also get good amounts of ALA from flax, chia, and walnuts. So what we've seen is that supplemental treatment using EPA and DHA can actually improve inflammatory conditions such as rheumatoid arthritis, irritable bowel disorders, and cardiovascular diseases. So again, supplementation is one thing. I will always recommend just improving your overall diet by eating the foods that are going to provide these nutrients. And then some of the vitamins and minerals that support healthy inflammatory response and therefore healthy immune system. Vitamin A supports the maintenance of our mucosal surfaces, so that's your innate immune system. Vitamin C and E act as antioxidants, right? So they help neutralize those free radicals. Vitamin D supports our immune system because it supports phagocyte production, so kind of a type of macrophage. And it also can support that anti-inflammatory pathway and seems to support a reduction in the severity of autoimmune disorders. Remember, zinc was also really important for genetic expression and enzyme activation, specifically for B and T cell proliferation. So zinc is really critical to the immune response. Selenium, remember, selenium is also a coenzyme for glutathione peroxidase, another antioxidant system. Selenium also supports B and T cell proliferation along with zinc. And selenium also supports production of those antibodies in the specific immune response. And then we have iron, copper, and manganese. These all work as cofactors for different antioxidant enzymes. And we see that a deficiency in any one of these also reduces the immune response. So they seem to also support that B and T cell functioning. And then interestingly, as we saw, too much iron can actually kind of turn around and have a reverse effect and can actually impair the immune response. And our gut flora is also closely linked to immune health and preventing illnesses. So remember we said that some of those beneficial microbes that live in our intestines, as they metabolize some of our fibers, they produce what are called short chain fatty acids, just like in our conversation about lipids. These are fatty acids that are short chain, so about 4 carbons in the chain. And what we notice is that these get absorbed by the gut enterocytes, and they actually seem to be mediators of the immune response and seem to be anti-inflammatory. So how do we maintain good gut health? Again, variety in what we're eating is one of the most important parts. Fiber, of course, is a critical important part of that. So getting fiber from a variety of different plant foods. Fiber is literally the food that these healthy gut microbes feed on. That's what prebiotic means. It's prebiotic before the bacteria. So it's the food that the bacteria feed on. Fiber is what gets fermented, thus resulting in the production of short-chain fatty acids. You can also consume basically living microorganisms by consuming fermented foods, such as kefir, which is like a fermented milk product, kombucha, tempeh, sauerkraut, and yogurt technically. Okay, so that is it for this chapter, for chapter 12. So as always, thank you for listening, and spend some time with these review questions here just to kind of test your understanding of the content from chapter 12. And also, as always, email me if you do have any questions. Thank you all for listening, and we'll see you for chapter 13.